Okay, now we've looked at a couple of different frequency plots, and we need to start talking about them more in general. One of the first things we're going to talk about is skewness. You can be positively skewed, negatively skewed, or relatively unskewed. These are the different ways in which a plot can appear. Positively skewed, negatively skewed, relatively unskewed. Let's look at the relatively unskewed one first. What that means is that we have a curve, kind of looks like a normal curve. It's just beautifully bell-shaped with no real skewness. Erase all ink. So, what we have here is the Young Turks. Here's their bowling score, a frequency plot of the score of the members of the Young Turks bowling team. And you see that a peak, the average score was about 150 to 180. They had some scores that were very high and some scores that were very low. With relatively unskewed data, the average will be where the most popular answer is found, or the most frequent response is found. So with relatively unskewed data, the average will be a great measure of the central tendency of the data that was collected. We're going to erase all ink again. That's relatively unskewed. I want you to contrast that now with the positively or negatively. Positively skewed has this long tail at a positive position relationship to the most frequent response. See the long tail positively displaced relative to the most frequent response. This implies that when I found the average, because I have this long tail, my average will be somewhere up here, even though my most frequent response was back there. So, with positively skewed data, you get a long tail to the positive side, the most frequent response, and it means your average response, x bar, will also be positively displaced in relationship with the true central tendency of the data. And that's the green tomatoes bowling score. Next, let's take a look at the red cabbage heads bowling score. See, it peaks very late, but had a long trail coming up to it. We'll call this negatively skewed because we have this long trail to negative numbers below the central tendency. It also implies that our average score would be less than our true central tendency here for the scores of the red cabbage heads. Those are three different kinds of skewness. It's important to notice skewness, and the best way to uncover skewness is just look at the data and say, what does it look like? Does it look relatively unskewed, equally trailing on both sides? Relatively positively skewed, where you got this long trail to the positive side, or relatively negatively skewed, where you get this long trail to the negative side of the peak. It's a very simple way of analyzing the data. And why is that important? With relatively unskewed data, the average does match the central tendency. With positively skewed data, the average will be greater than the central tendency. With negatively skewed data, my average will be less than my true central tendency for the data. That's skewness. The next thing to take a look at is kurtosis. Just as we had three kinds of skewness, we have three kinds of kurtosis: mesokurtic, leptokurtic, and platykurtic. The Young Turks are somewhat mesokurtic, meaning they slowly rise up and slowly rise down. It's this beautiful little bell-shaped or normal curve related to the data. So we call that mesokurtic, or the kurtosis is in the middle. Meso means middle. And it's mesokurtic type plot of the frequency of bowling scores for the Young Turks. We took a look at the leaping beans, and you see how it's relatively flat and then peaks up really high, and then flat again. So it's really peaking here. It's leaping up, and we call that leptokurtic, whenever it just really is concentrated at a particular place, and leaps up there. Platykurtic, in contrast, is flat. So here's the platypus's bowling score. It is basically flat all over the place. It really isn't fair to say the average score is 150 to 180 because the scores went all over the place. While this may be the average, the numerical average, that doesn't really tell you a lot about the distribution of the data. So we have three different ways of looking at this data in terms of kurtosis. Mesokurtic, it's in the middle. Think like the French, meh, or who cares? Meh, it's in the middle. Mesokurtic, nice bell shape. Leptokurtic, as your mnemonic, remembers it leaps up. So it has flat, leaps up, and then flat again. Leptokurtic, very concentrated. Platykurtic is flat like the bill of a platypus, and it's just flat distribution of data. So these are three ways in which to describe the kurtosis of the data. Kurtosis says how concentrated the data is, whereas skewness, back here, describes whether or not the average and the central tendency are actually aligned. Does it have a long trail positive relationship to the most popular answer, a long trail negative relationship to the most popular answer, or relatively similar trailing on both sides? All right, so let's take a look now at central tendencies. Central tendency. There we go. And we have, of course, the idea of the mean, which is the arithmetic average. The standard way to calculate the arithmetic average is you have these individual points, x sub i's, these are the individual answers that you got, or responses that you have. You add them all up, so you take the sum over all of the points, I, as it goes from 0 to all of the points, n, and you divide by the number of points in the data set, n. And that we would call the arithmetic average, which is often denoted by x mod. That's our arithmetic average, the one that you probably are most familiar with. There are two other averages as well, or measurements of central tendency. One of them is the median, and that is the one in the middle. Finally, we get to the next one of mode, and that is the one most common. So, for instance, if you have a distribution, looks like this, you'd find that the average would also be the most common and in the middle. They all match when it's a nice normal bell curve. But when you have some of those forms of other data, like for instance, positively skewed data, you'd find your average, your arithmetic mean here, even though your most common answer, or your median, is there. I'm sorry, the mode is there. The one in the middle may be somewhere around here, the median. So in this case, with positively skewed, you find that the average, the arithmetic mean, is greater than the actual mode. Whereas with negatively skewed data, it goes up like that, you find your average is down here somewhere, where your mode is there. So it is now less than my mode. You'll see three ways of looking at our central tendency, or our mean. The next thing we looked at was also kurtosis, not just skewness. You see how skewness affects our measurement of our central tendency. We also looked at something called kurtosis. So kurtosis kurtosis, a measurement of how spread out things are. Well, how do we measure how spread out things are? Well, first thing we can do is look at the deviation in the data. And that's just simply where my individual point is, less my average, my arithmetic mean. Each point will have a different deviation. Some will be positive, some will be negative. But if I add them all up, I'll find that the sum is 0. Because I have just as many above the average as I do below the average. And, well, the average is in the middle, so it always sums to 0. So the deviation, I can't just sum it to find the deviations or the spread of the data overall. What I'll find is the standard deviation instead. And the standard deviation for a sample is denoted by S. And that is going to require that I add up all of the points from I equal 0 to n, or 1 to n, of my deviations. And if I just add them, I'll get 0. So I will square them. Now I'll divide by the number of points in my sample less than 1, because I used 1 degree of freedom to find my average here. Finally, since I took the square, I will now take the square root. And that is my sample standard deviation. For the entire population, it's a very similar formula. The sum of the deviations squared divided by the n. So it's a very, very similar formula for the population standard deviation. So we have our average, our arithmetic average, as the sum of the positions divided by the total, and our sample standard deviation as the sum of the individual data minus the average squared divided by n less 1, and we take the square root of all of this. Great. This is fine if we have raw data like we did for the distance traveled to school. But what if we have summary data? We can't quite use it in this format. In the summary data, we're given the frequency of a response and the response itself. So to find the average with summary data, you take the sum of the products of the frequencies and the responses, and you add those up and divide by the sum of the frequencies of responses. This is the weighted average for tabulated data or summarized data. Now, let's think about probability. We can also do this in probability. If you recall probability, I'm going to write here, probability is just simply the frequency of an answer. Probability of getting an answer is the frequency at which you got that answer, divided by the sum of the frequencies of answers. So, this equation here, this divided by that is basically the probability. So, if I have summarized data, but not the individual frequencies, I can just write this as the sum, the probability of a response, times the value or the meaning of that response. So here's a weighted average given frequencies and a weighted average given probabilities. Two ways of calculating the average when I'm not given this raw data, but rather summarized data. You'll be using weighted average quite a bit. Great. Well, that's my average. What about this sample standard deviation? Well, we need to think about that. Now, what about finding the sample standard deviation when given summary data? Well, our sample standard deviation would be equal again to the same square root of Let's take the denominator first. N is simply the sum of my response frequencies, less 1, because I took n less 1 over here. And now let's look at the numerator. I still have my differences, my deviations, x of I minus x bar squared. And I'll have each one of those represented the frequency, the frequency of response times. So given summarized data, I can calculate my sample standard deviation using this formula. That's given frequencies. Again, what if I have probability? Well, there, let's take a look at this equation. There's my frequency here. There's my frequency there. I need to know how large my sample size is. Because here, it's saying probability of getting responses, the frequency of that response over the number of response. So frequency of response is the probability times n. I can use this equation here, find that my sample standard deviation equals the square root of the sum of x of I minus x bars squared. Now my frequency is simply my probability of getting that response times the number of responses in the sample, and my sum of my frequencies is my n less 1, divided by n less 1. So basically, I have my sample standard deviation is the sum of the sum of the x of i's minus x bars squared times my probability times this ratio of n over n less 1. And I rewrote it because for large n, like suppose n is equal to 100, n equals 100, this n over n less 1 is about 100 over 99, which is about 1. For large n, you'll find that this portion is not necessary. So you can say S is approximately equal to just simply that part of the equation. The square root of the sum of the deviation squared times the probability of getting those particular responses. It's a shorthand method of calculating our sample standard deviation. I'm going to go back into Excel, show you how we can use this for some data.